Okay. Hello, everyone. Walter Gordon here, chairman of the AIAA Niagara Frontier Section. I'm going to babble for a few minutes because I never know how long it takes for all the people to enter the talk. And meanwhile, I'm going to pull up a slide, hopefully. You guys have a full screen slide?
Nothing yet.
No? Oh, wait, I got to hit the share button. You think because I do this once a month, I'd have it down.
Better you than me, Walt.
You got a slide yet?
Yes, we do.
Okay, so I'll start babbling about this, then we'll introduce our speaker. Upcoming webinars, we'll probably have something in September and November, but they're not determined yet. October, Carol Ann Adams is the executive director of the Glenn Curtiss Museum in Hammondsport. She's going to talk about the Curtiss Cadets, which was a program during World War II to take women and train them not to be Rosie the Riveters, but to give them a one-year intensive course to make them entry-level engineers. And I never heard of it till Carol Ann told me about it. So I'm really looking forward to hearing that talk. It sounds fascinating. And it was done by Curtiss Wright, which is why she's doing it as director of that museum. December, we have Bill Suter, who was one of the original Bell Rocket Bell pilots. If you saw Sean Connery flying it in Thunderball, that was a composite of several flights, but he was flying one of them. He also flew the rocket belt in the '84 Olympics and was one of the original rocket belts test pilots. So he'll be coming to us also. So far as ROE today, suggest you hide non-video participants and select single speaker during the talk. Don Nixon and I, my backup host over here, will both be going mute and turning off our cameras. Rules of engagement, submit comments or technical issues via the chat, submit questions via the Q&A. And if you're looking for a recording of the talk afterwards for yourself or friends, send it to the email address you see here. Do not reply to the invite you got. So send it to nf.aiaa@gmail.com. Normally, I don't bother to introduce our speakers at all because I say you all got the brochure. But sometimes their qualifications just demand it. And someone with 3 master's degrees, including 1 in aero engineering, top graduate of his test pilot school class at Edwards AFTPS, and almost 200 combat hours in the F-22, that deserves a little bit of introduction. So there you have it. And now I turn the talk over to Tucker Bobsled Browne. It's all yours, Tucker.
Yeah, thanks so much. All right, I'll share my screen. 1 second. All right, how's that look?
You're there, you're full screen.
All right, outstanding. Hey, thanks everybody for having me. Thanks for showing up here. My name is Tucker Browne. I'm a major in the Air Force. I go by Bobsled, so I always have a hard time introducing myself. Don't know what to say to call me. I'm glad to be here. I appreciate the opportunity to talk to all of you. It's always fun to chat about something that's really cool. And one of those things is the F-22 flight controls. So my personal background, I finished undergraduate in 2011. I had a BSc in mechanical engineering, material science. I went to Cornell in 2012. Didn't know about the AIAA chapter that you guys are running over here. Wish I had, where I got a master's of engineering. And then I was in the Air Force for 8 years before I got picked up for test pilot school. I went to test pilot school in 2020. Got another master's in flight test engineering. Got to fly a bunch of really cool airplanes. At this point in my career, I've flown 30 aircraft types, but primarily I've spent most of my time in the F-22 and then a bit of time in the F-16, a couple hundred hours. About 200 combat hours in support of Operation Inherent Resolve over in Syria, and then hundreds of test missions doing developmental tests and operational tests in the F-22. But big picture, who do I think that I am in the Air Force? I think that I'm a test pilot. So I'm a combination of an engineer and a fighter pilot. And I like to think that I do both, but I probably don't do either as well as the individual roles. I like working on new things, and that's the role of a test pilot. It's different than being a fighter pilot who spends a lot of time training for operations and tactics and figuring out how to best employ the aircraft. I did that for 5 years or 6 years in the F-22. And then I had to shift that mentality when I became a test pilot. And then it became, how do I defeat this, or how do I manage risk to get data to advance technology? And that's been a really interesting change. And I really enjoyed getting to employ my background in academics and engineering, which I didn't get to do as much as just a fighter pilot. So flying for me is a passion. Out of those 30 different aircraft, I've flown things like the F-15, the C-17, you know, standard Air Force things. Flown older aircraft, the P-51, the B-17, the T-6 Texan 1. They got to do a loop with the canopy open. That was pretty sweet. Flew the T-33. I've flown a few helicopters, KC-135, and my absolute favorite was a flight in the A-10, where that's a single-seat airplane. And test pilots get the luxury of not having to be qualified in airplanes to get to go fly alone. So we got to go out, a set of me and 3 other test pilot school guys, take an A-10 to the range, having no previous experience, and got to shoot a 30mm gun, never shot a gun at the ground before, shoot rockets, and fly to 500 feet. That's something that I'll never forget. But in the big scheme of things, it's actually pretty normal in the world of flight tests. So you might wonder, hey, why do test pilots actually fly all these different airplanes? And in reality, the test pilot bios you see, they'd love to put the total number of aircraft that they've flown up here. In reality, flown most of those airplanes one time, maybe 2 times. It gives you a feeling of differences between aircraft, which helps whenever you're developing things like flight controls. I started flying little planes in Cessnas. I still do, and I really enjoy it. One of the most interesting things that I find, though, is that things that I have learned in Cessna 172s is still applicable to testing flight controls, even in fly-by-wire jets. Didn't mention it. This briefing is obviously unclassified. Feel free to ask questions as you go through. There's obviously sensitive things about the F-22, and if we can't answer it, we just won't answer it. But I've already cultivated the brief to what it needs to be, and we can talk to anything that I have up here. So the F-22 Raptor, I think it's the coolest airplane you can fly. Sometimes people will ask me if I wish I was an F-35 pilot because it came out more recently, and the answer is absolutely not. Like, this thing goes Mach 2. The F-35 can go Mach 2 as well, maybe if they're going downhill. It's 9G capable. F-35 says it is too, but maybe not as 9G capable. You go above 50,000 feet. It's stealthy. It has super cruise, and it has a really sophisticated fly-by-wire flight control system. We'll get really into some of the specifics of that flight control system, but that's something that really sets it apart in its mission of air dominance. It allows it to achieve super maneuverability, and it allows it to reduce workload for the pilots by integrating control surfaces and thrust vectoring. So realistically, flying the F-22, I often say, is significantly easier than flying a Cessna 172. It's one of the easiest airplanes to fly, maybe in the Air Force, which is probably why the Air Force let me do it. So in the original Dash 1, of which the Dash 1's the flight manual for the F-22, they went bold. They wanted to make the greatest fighter pilot airplane they could ever make. And they even put in the term, can be flown with reckless abandon. And what they meant by that is that the pilot doesn't have to consider things like over-G or stalling or going out of control or spinning. Originally, it was designed to be flyable without pilots really having to think about anything in a tactical situation. Instead, you just focus outside. If you need to move the nose, you pull back on the stick. Even if you're past the stall alpha, it'll just continue to move the nose. If you're really fast and you pull the stick all the way back, it'll limit you to the G's you're allowed to go to, right to the edge of performance. And it actually turned out that that was mostly true. You pull back on the stick all the way, it will limit you to exactly what will not negatively affect the jet. It's essentially unlimited alpha, or angle of attack, with virtually no chance of departure. In fact, I've gone out as a test pilot and tried to depart this airplane, and I've never gotten to, which is a bummer. But a couple people got kind of close, which is why they took that out of the Dash 1. Probably not the best idea to promise something like reckless abandon when you have dumb fighter pilots flying airplanes. So how is it possible? And that comes into the flight controls. And that's kind of what I'll focus on for this brief. I'm just going to give you the top picture of, hey, what is different about F-22 flight controls? There's a lot of things that are actually contained in F-22 flight controls that exist in other aircraft nowadays. And a lot of technologies are shared. Even like fly-by-wire systems like the A320 share a lot of similarities to the limiters and the reckless abandon perspective that the F-22 has.
Yeah. Tucker, if you want to take questions during, we just got one. How is it for spin recovery? Was the specific question.
Can you see that chat thing on my display? Are you seeing just the PowerPoint right now?
Just the PowerPoint, that's correct.
Okay, perfect. Yeah, I got the chat up as well. Okay, yeah, so for spin recovery, and I'll talk a little bit for it later. The big things are spin recovery. I've never gotten into a spin. So even whenever you intentionally bring it up to stall and put in really large pedal asymmetries, or you intentionally aggravate the stall and you try to actually induce yaw, the most you'll usually get out of the Raptor is maybe 1 or 2 roll-ups, and then it will recover itself. In fact, the out-of-control recovery procedure for the F-22, actually, the out-of-control recovery procedure for most fighters in the Air Force, because most of them actually have a pretty good digital flight control system, is to go throttle idle and take your hands off the stick and have it fix itself. And if it doesn't do that, there's a couple other steps that you'd have to do, but that solves it 99% of the time. And the Raptor is actually very similar. It's just in the Raptor, you actually go throttle to mill. So you put the throttle up to not afterburner, but in full power. So that way it can give you thrust vectoring to help with spin recovery or any sort of departure or out of control recovery. And then you take your hands off the stick. And every single time it is recovered extremely quickly. It is absolutely one of the most safe airplanes to fly. You have a really tough time putting yourself in a bad situation. All right, so getting back into, all right, sweet. So you guys, I'm sure, probably know what a stable aircraft is, but we'll just do some basic review right here. So stable aircraft is traditionally, this is a really easy force moment diagram. The center of lift is behind the center of gravity. Essentially, and with a relatively small downward force in the tail, it'll counteract the moment. The biggest thing about this configuration that's good is that upward pitching, increasing your angle of attack, will increase lift, which then causes the nose to try to turn back down. It'll return to neutral, resulting in positive static stability. That is not the case for a fighter. So in most fighters, lift is forward to the center of gravity. So now when you increase the angle of attack, it increases lift and causes a further nose pitching up moment. It's unstable. So now what you have to do is you have to have digital flight controls to counteract this to reduce pilot workload. In some cases, if the pilot wasn't really actively fighting this the whole time, and sometimes it's even impossible to do that due to considerations like pilot-induced oscillations, the airplane just wouldn't be able to fly. So the F-16 was one of the first unstable airplanes that was actually invented, or not invented, but operationalized. And just an interesting tidbit, I often hear people say that aircraft are made unstable, or the F-16 was made unstable for maneuverability purposes. And while maneuverability does actually increase somewhat due to unstable or instability like this in pitch, it actually wasn't why it was first designed or implemented. And it's because of the tail force. And the thing that you'll notice that's different there is that as opposed to a stable aircraft where the tail force provides a down force to counteract lift, in an unstable aircraft, you can have the wings and the horizontal tails provide an upward force, which means now you have more ability to have lift, which increases performance because you need to fly at a lower angle of attack. So initially it was made literally to increase the range of the F-16. They said, oh, this is actually really great for maneuverability too. But I didn't know that until I got to test pilot school. I always thought the F-16 was designed to be unstable. And then some of the original F-16 testers told me that. So I thought that was pretty interesting. So what you have to do when you have an unstable aircraft is you have to do some sort of fly-by-wire or digital flight control system. And essentially what that does is it gives you a flight control computer that talks to actuators to automatically actuate your control surfaces. So most advanced fighters, most of which are inherently unstable, which there's exceptions to that. For example, the F-15 is actually a stable aircraft. But for inherently unstable aircraft, they require flight control computers to make the workload reasonable. So one of the things that happens there is it gives sort of feedback. So now I am just giving a vote to the computer as to what I want to do, but it allows for much quicker flight control responses, and it allows for some cool things in that now if I just pull back on the stick, it doesn't necessarily just directly connect to an elevator the way that it would in a Cessna or some sort of small pulley driven airplane. It can do a combination of different flight controls. And also another misconception I had, at least coming into test pilot school, is that, hey, if an aircraft's unstable, that means it's uncontrollable, and that you'll just go out of control. There's no way for a pilot to fly an unstable airplane. One of the coolest things I got to do in test pilot school, I got to fly the X-62 Vista, which is a specially designed F-16 that allows it to basically modify the flying qualities of aircraft. And I also got to fly in a specially modified Learjet run by Calspan that does that too. And one of the things they did, they added a pitch instability into it. So now as the nose starts coming up, it actually keeps going up. And as the nose comes down, it keeps going down. And I thought this is going to be pretty difficult to fly. It turns out it just takes a fair amount of pilot workload. You can fly an unstable airplane, which I had no idea that you could control it. But you can. So the traditional kind of flight controls in stable aircraft, sometimes you might see reversible flight controls, i.e. pulley sort of systems. So airplanes like Cessnas have these reversible flight controls where you move the stick and the flight controls move. You move the flight controls and actually the stick moves as well. That means you have to consider other factors into flying qualities and handling qualities, such as wind, speed, aircraft loading, buffet, because now you're going to feel those forces on your control stick and it's going to affect your ability to fly the aircrafts. Lose a slide. Yep, that's right. No. So a couple differences between what we've seen here. So for some basic flight control differences, in a reversible flight control system that doesn't have a digital flight control computer, the faster you go, the more sensitive flight controls can be, and the higher control forces required. And that is okay for things that operate essentially from 50 knots up to maybe 150 knots, where the relative forces on the control surfaces are not that different. It's not okay when you're going Mach 2 or you're pulling 9 Gs. And in those cases, you actually need the ability to have some sort of boost system in there, and irreversible flight controls help a lot. And the way that we do it in modern fighters nowadays are hydraulically assisted actuators. So the F-22 has a very, very strong hydraulic system with a ton of redundancy, because if this goes out, I can't control the flight controls. So we got 4,000 PSI hydraulics. So as a fighter pilot, if you just touch the stick on the ground, your flight controls, you'll have this giant flat slab of metal that moves around. So every time you've got maintainers near you, you're always hands off, showing them that it's safe for them to walk around. People really get really touchy about the fact that those things are so powerful. But that's what enables a lot of the actual pitching forces, rolling forces, and maneuverability that exists in these aircraft. Additionally, these specific ones are electrically controlled. The way that they're electrically controlled is the engines in the F-22 have permanent magnetic generators. So as long as the engines are rotating, even if they aren't actively being powered by fuel, they can just be windmilling. That's enough power to continue to power the flight controls. If those engines go out and your permanent magnetic generators go out, one engine would be fine. If both of them go out, then you got to back up via the batteries and electrical buses, but you don't have a lot of time. So you still need electronics, you still need hydraulics. So getting into the F-22 surfaces. So typical aircraft have elevators, ailerons, rudders, flaps, maybe speed brakes as well exist in some aircraft. The F-22, it adds flaperons, which are similar to flaps, but can be used for roll control as well. It adds angled rudders. So instead of the rudders or tails being, angled rudders, rudder vaders per se. Instead of the tails being straight up like they are on the F-15 or the F-16, they're canted on the F-22. That allows the actual rudders to provide pitching moments and rolling moments potentially, in addition to just yawing movements. We added vectoring nozzles in the F-22, and it's the first operational fighter to employ those. And that is what makes the air shows so great, if you guys have ever seen them. It allows you to do things like high alpha loops. So in a typical fighter, it might take 5,000 to 10,000 feet to do a loop. In an F-22, if you're trying to do a high alpha loop at slow speed, you can do it in 1,000 feet, which is pretty amazing. And you can actually be entirely stalled and still get your nose back up, which when it comes to things like, or you can be past, when I say stalled, I need to retract that a little bit. You can be past maximum coefficient of lift and still move your nose up. We don't actually talk about stall in the F-22 the way that you would talk about it in other aircraft, because the F-22 doesn't stall the way that other aircraft stall. Most aircraft, when you stall, you'll have something like a wing drop, or you'll have your nose fall, or you'll have some sort of buffeting occur. The F-22, you can actually not even notice that you're stalled. What happens once you get past a certain angle of attack, the flight controls take over, and they are just going to keep moving your nose and commanding the same pitch rate that you need to command. They'll be using thrust vectoring. They'll be combining in the leading edge flaps, the flaperons, the tails. They'll get everything they can to keep your nose moving. And young guys that are flying the jet, we call it going off the skateboard. What you'll do is you'll be staring out, looking at somebody, trying to get your nose on him to gun him. You'll pull all the way back on the stick. And what you really want to do is hit that best max angle of attack, max perform, maximum coefficient of lift, and hold that while you're looking at this guy. But what they'll do is they'll hold the stick all the way back, blow past that, get a ton of nose pitch rate, find themselves down at like 50 knots. And then after that, you kind of just have to fall out of the sky and regain some airspeed. But you don't get a traditional stall, which is pretty cool. Additionally, the flight controls even include things like inlet bleed doors. We have really advanced engines that work really well. One of the interesting things in the F-22 is that it was designed for stealth. So the F-15 or F-16, well, aircraft like the F-15, they have inlets that actually potentially change shape to modify basically where that shot cone hits the face, so that the shot cone doesn't hit the face of the engine. The F-22, because it's stealthy, we don't want things moving up there. So we didn't do that. So it's just a fixed inlet, but it's so well designed that I've never heard of anybody actually have a compressor stall, which is crazy, because in the T-38 and every other airplane that I've had, happens all the time. I've never actually lost an engine, and I've only heard of one guy having to shut one down prematurely. There was one time where I had to pull it back to idle over Syria, which was a little bit disconcerting. But that's the worst thing that's happened. So for these surfaces, all of them are controlled seamlessly via digital flight controls in the FADEC. The computer inside there knows exactly what I'm commanding, and it will use what makes sense to give me what I want, whether when that comes to pitch, G, roll, yaw, beta, whatever I'm asking for, and I don't have to think about it. Additionally, well, actually, we'll talk about the flight control actuators for the pilot in a little bit. So the cockpit design, you've got a traditional fighter on the left. That's an F-15. It's an older F-15. It doesn't have any digital displays. Newer ones have digital displays, but where the stick is and where the throttle is are about the same. So the stick on the F-15 you'll see is a center stick. The F-15 is actually a hydraulically actuated, but not digital flight control aircraft. The F-15EX will be a digital flight control aircraft that's hydraulically actuated, but it'll look very similar. On the right, you have the F-22. The F-22's got the throttles on the left, which are about in the same position, and it's got the stick on the right. And there's some questions as to why would you want to do that? Really, it just comes down to what you're used to, honestly. So a lot of the Air Force fighter pilots get trained in the T-38. T-38 is a center stick. So some guys like the center stick. It works fine. Some guys like the side stick. The side stick works fine. F-16, F-22 have side sticks. Some commercial airliners have side sticks. Some don't have side sticks. They enable better visibility. You can see the displays on the right are significantly easier to see. And there's even a fold-out armrest, which allows you to actually get some leverage with your pull, which is pretty cool. The other thing about the side stick, though, that's different is that it can't move as much as that big center stick. The big center stick actually can be pulled all the way back to the seat pan, or it can be moved over to the side. So pilots have just a different feel for it. So it just changes the handling qualities a little bit. But out of everything I've flown, I think the F-22's design from a cockpit design perspective is the best I've seen. So the side stick design, it originally actually didn't move at all. It was just a fixed stick that, oh, all right. Sorry about my dogs. It was a fixed stick that was just a force sensor. So it was just a piece of metal that looked like that wouldn't move back or forward. It would just feel how much you're moving the stick. But it was problematic. Without any movement in the stick at all, it was actually really easy to pull the stick when you didn't want to or roll when you didn't mean to. I found this in the F-16 because I flew the F-16. And the F-16 wasn't quite fixed, but it was much more fixed than the F-22 stick. Sometimes I'd be looking down, working on a task and thinking I'm flying the aircraft, and I wouldn't even notice that I would be rolled 90 degrees to the left, which was pretty crazy, actually. So the F-22 got past that by adding in more realistic control forces. They made a compromise between the F-15 idea where you can move the stick a lot and have good SA on or situational awareness on where the stick was in relation to you by adding in a 1/4 inch to a 1/2 inch in each direction. Additionally, they added things in like a soft stop and a hard stop. You could pull back with about 25 pounds of force and hit a soft stop, and about 50 pounds of force hit you all the way back to the hard stop. And between each of those levels of stops and each of those levels of force, there's control laws, and we're not always linear. Pulling aft on the stick would give you a linear increase to a certain point of G, and then pulling further aft past the soft stop would actually be a more highly sloped line. And it turned out that they designed this really smartly to give the pilots the best feel for what a regular airplane would feel like, i.e. in a Cessna, when you pull back on the stick initially, your initial control forces are relatively light because you're not fighting the wind or you're not putting a lot of forces on the control surfaces. But as you pull back further, they actually increase. And this gave us some of that feeling. So the side stick design is a bit of the best of both worlds. It's enough to feel more realistic, but it's compact over on the right side, which leaves a lot of real estate for displays and the real purpose of the jet, which is tactical employment. So a little bit into the pilot flight controls. You can see the control surfaces are on the right again. So the pilot doesn't move the elevator. I don't change the aileron to put in rudder. Instead, I just command the aircraft to do what I want it to do when it comes to roll, pitch, and yaw. In the pitch direction, when you pull the stick back or push it forward, depending on your airspeed, it changes from pitch command to G command and back and forth. And that actually was a pretty tough thing originally in the F-22 program, because moving from G command to pitch command as you slow down, for example, it could get a little bit disorienting. So they had to use a lot of very specific control laws and control law tailoring to make it seamless. And it really is. Like, you don't notice when the control laws change. Another really interesting one is the yaw command. If you've been to the air shows, you might have seen them do these pedal turns where, can you guys see me actually as well?
Yes, we can.
All right, perfect. Or you would actually yaw the jet just around a point. So if you're going fast, actually all it commands is just a little bit of side slip. But as you get slow and you increase your angle of attack, it will command just the jet to rotate, which is pretty amazing. You can't get that yaw out of any other aircraft before the F-22. The F-35 flight controls are actually pretty similar to the F-22s. So the jet knows the best way to get what's commanded. It combines flight controls and thrust. So I'm talking about that pedal turn that happens. So for the pedal turn, you get up to a high enough angle of attack and slow enough speed, you put in pedal to the right, we don't even call it rudder, and it starts this yawing moment. So that yawing moment might include the rudders going one direction. They might go symmetrically. They might go anti-symmetrically. Your ailerons are going to deflect maybe both the same direction, which that doesn't happen in traditional airplanes. Your flaperons will also go into place. Your leading edge flaps, one will dig in, one won't. Your horizontal tails will go opposite, which will start actually commanding a roll moment or at a high enough angle of attack, a yawing moment. And the ability to employ all of these together is what actually allows the aircraft to have stability throughout basically the entire angle of attack envelope. Other fighters like the F-16 are actually alpha limited. So for example, in the F-16, if you get above mid-20s in alpha, you have a high risk of departing. And the reason for that is because as you increase your angle of attack to here, the airflow that's going over your wings doesn't hit your tails. So you lose basically yaw stability, and you have a high chance of going into some sort of spin or out of control situation. The F-22 avoids that by using thrust vectoring, anti-symmetric things and horizontal tails and flaperons. And it's pretty amazing that it is actually stable from a digital flight control perspective throughout the entire envelope. Additionally, you might notice that there's no speed brake on the F-22, and that's true. And when you put out speed brakes, what it does, it just takes those rudders, puts them out in the wind, takes your ailerons, moves them up, takes your flaperons, moves them down. It just throws out whatever control surface it needs to put in there, but it doesn't provide any pitching moment, any rolling moment. It's just as if you put out a regular speed brake like you would in any other aircraft. All right, got a question. Given all the aggressive angles, maneuvers, G-forces, and such the craft is put through, how is fuel flow maintained under any and all conditions? Yeah, so these engines are amazing is how. Thank you, Pratt & Whitney, for making the best engines that I know of. I would say that the pilots here, like, it is extremely impressive that the F-119 can operate essentially at 0 knots, which doesn't happen. It can operate at mil power and all the way to AB at 0 knots, which can be difficult. You can go from afterburner down to idle power without risk of compressor stall or flame out. And the way it does that is through a very effective FADEC or a digital engine control. Can't remember what the FA stands for, but the digital engine control will keep you safe, essentially, is what happens. So for example, if I'm really slow and I try to pull the throttles all the way back to idle, it might not let me do that. I might command idle, and it might just keep the throttles up at near mil power. Or if I'm really, really fast and supersonic, it might do the same thing. As I'm pulling the throttles back to avoid any sort of issues decelerating from supersonic speeds, it will just maintain a minimum RPM or minimum fuel flow rate. We have a great fuel pump on the airplane, and essentially it's just a FADEC that is also just as well designed as the flight controls that enables the engines to be really effective. So the thrust vectoring, the F-119 that we're talking about, 35,000 pounds of thrust with the afterburner, absolutely amazing. The thrust vectoring, some people ask, do you pull the little thrust vectoring stick or something? There is no thrust vectoring stick, actually. It's all automatic as well. Essentially, it activates in a couple of different domains, especially low speed and at high altitude. So the low speed reason for it activating is once you get below aerodynamic flying speed, which for airplanes like this is somewhere in the realm of 100 to 150 knots, you need something else if you want to continue pitching the aircraft. And what you'll see over on the right-hand side of this display is the F-22 demo team. They made this pretty sweet collage. Oh yeah, thanks, Gary. Full authority, digital engine control. They made this sweet collage of a demo pilot going up, doing a roll, and then doing a high alpha loop. And what you'll see is that this loop is extremely tight, and his nose actually continues tracking. You can get your nose all the way back up to essentially level with the horizon as he does a pedal turn throughout. And that's entirely because the engine is taking 70,000 pounds of thrust and attaching, some amount of angle to that to push your nose up or down, whatever you need. So that's the low speed use case of it. You get really slow in a slow speed or you're doing some sort of vertical maneuvering and you need to move your nose. You'll kick in the the thrust vectoring is what will continue the pitch movement. And then high altitude, actually, there's some usage for thrust vectoring, which I didn't think of before I got into the jet. When you're up at 50,000+ feet, it turns out the atmosphere is pretty thin. So even just having the ability to kick the nose up a little bit using thrust vectoring is really helpful at just being able to fly comfortably up there. So it automatically kicks in up there. And that is a really cool capability. So how does it look for folks that are actually flying the aircraft? So on our display is one of the displays that we always fly with when we're doing basic fighter maneuvering, which that's whenever we're going out there to dogfight, or if you're out there doing flight test for flight control sort of testing, you'll have a thing up for the control surfaces, which is actually a pretty cool display. Initially, this display, the flight control display, was made just for flight tests. It was supposed to be taken out whenever it was getting to the operators, but the test pilots thought it was so cool in the YF-22 and the initial F-22 that they kept it in. It shows your center of gravity. It automatically will show you if you're in a position that's bad. It turns red, pretty easy for pilots like me to understand. On the right, bottom right, it shows where your stick is in relation to center. So in this case, you have your stick forward and to the left. So you're commanding about half of roll and half of forward pitch authority. At the bottom, it shows you your rudder position. And then there's leading edge flaps. There's thrust gauges for the engine. You'll see there's like a little tick mark on the outside. So there's an arrow and a tick mark. The tick mark's what you're actually asking the jet to do. And then the arrow is what it's actually doing. So that might be a case where you would ask it to do something and it wouldn't let you do it. And then up at the top, there's examples of where all the control surfaces are at. And you can see that regularly flying this thing, that everything is just going in directions that don't necessarily make sense. All right, Benjamin Suarez asked, why was it determined to have 2D thrust vectoring nozzles compared to 3D thrust vectoring capabilities? So the long story short is the juice just wasn't worth the squeeze to have 3D thrust vectoring. 3D thrust vectoring would be helpful. So some aircraft like the Su-35 and some other Russian aircraft have shown 3D thrust vectoring. We actually had, I'm going to get this wrong, and I'm sure you guys would know. I think it was X-29. There's an X-plane that also demonstrated three-dimensional thrust vectoring. And it does give you some ability to maneuver, but in reality, for a fight with fighters, the pitch axis is much more important. And one of the things we had to balance in designing this aircraft is stealthiness. Making a three-dimensional nozzle that's stealthy as well is difficult. But for a two-dimensional nozzle, they found a way to do it. So that's essentially why it was. You got most of the benefit using 2D thrust vectoring, a little bit less complexity in design, and you can maintain stealth. So what happens if you lose a flight control? One of the coolest things with this airplane is you don't really have to think about it. In other airplanes, you would have to trim. You almost never have to trim this jet, which is also very weird because almost every other aircraft I've flown, you have to trim. If you lost a flight control, it would just show, hey, there's an X over this. Your left aileron's not working because maybe some hydraulic issue that self-isolated happened. And then it would pull up a little checklist for you. Jet's awesome. It has its own checklists. It would say, hey, your max landing speed's reduced by or increased by 6 knots or something. No changes to flying qualities. Good luck. If you lose 2 or 3 flight controls, the same sort of thing. It'll just tell you what changes with your airspeed, but the aircraft is still flyable to very acceptable handling qualities that basically don't demand significant changes. Once you lose enough, then yeah, you want to stay in what's called the FLICUS happy place, the flight control system happy place. So that's when you'll lose the ability to maybe go all different angles of attack and all airspeeds. But it's a really cool redundant system that allows the pilots to not really think when things go wrong. Instead, you just get to think about employing the aircraft. So Joe Travato asks, is the center of gravity calculation automatic or some type of manual weight and balance entry to get this displayed? It's entirely automatic. So the aircraft has internal weapons. It will know what's loaded on there via a stores management system, and it will add the weight of those internal weapons. It'll add the exact weight of their fuel, which is split into 10 or 11 different fuel tanks in their exact positions. It'll assume the weight of the pilot. So I guess that's the one thing that's slightly off, but that's not that big of a deal. And then it will calculate your center of gravity. Your fuel system will automatically maintain your center of gravity exactly where it's supposed to be. It will balance the lateral by moving fuel between the left and right wings, for example. It'll manage the longitudinal by feeding fuel out of the correct system. So that way you're feeding evenly from the front and aft. And it's automatic. Justin asked, do the vector nozzles always move in tandem, or can they impart a roll moment? They do actually always move in tandem. So you're right. There's the one thing that's not automatic in this one. It basically just goes both up, both down. I don't know why.
And you had one more question above Joe's, if you
Oh,
click.
yep, thanks. Jimmy Lee asked, are the stick input directions pitch and roll? If so, how is yaw commanded? So yes, what you see on that green display down on the bottom right, there's the blue dot that's moved up into the left. So forward is your think of your pitch. So this is pitching down and pitching and rolling to the left. The yaw is down at the bottom. So you see that bottom straight line that has a blue dot in the middle. That just means that there's no pedal input in. If you put pedal in, then that would move to the right or left. But we have pedals the way that traditional aircraft have rudders. Sorry for missing that. Okay, so a few more things about the flight control. So on takeoff, the flight control system has very smart mode switching. So you can imagine that the flight control gains and maybe even the flight control modes at different phases of flight should be different. So takeoff and landing are actually very similar. Weight on wheels means you're in takeoff mode. If your gear are just down and you're below a certain airspeed, you're in landing mode. So on takeoff, your rudders will actually both toe inwards, which is a little bit weird, but it actually causes the nose to pitch up. The ailerons will move down slightly. The flaperons will extend. The leading edge flaps will also move down to create a lot of camber and essentially give you flaps that you would have in another aircraft. The takeoff occurs at about 150 knots, or if you're an afterburner, a little bit faster than that. And it's really seamless switching up to cruise and going gear up. On your landing mode, the pilot does nothing. As soon as your weight on wheels, it'll bring both your ailerons up. It'll bring both your flaperons up. It'll bring your leading edge flap back to nominal to kill the lift. Additionally, it'll deflect the rudders anti-symmetrically. And then the brake system is extremely effective in this airplane, which allows for very quick stopping. Sometimes too quick. I remember I landed heavy out in the desert one day on a hot day. Didn't realize how much fuel I had and wanted to stop. And the jet let me stop, and my tires caught on fire, which I got made fun of for quite a while. So don't do that. Air refueling mode is another mode that occurs. There's a small switch just in your cockpit that opens up the door on the top, but it doesn't just open the air refueling door on the top, it also changes the gains. It reduces the roll capability. It dampens your pitch response. This is a very fine tracking task that pilots are doing. You're flying, 20 feet away from another aircraft right underneath him while he's hooked up to you. You don't want your stick inputs to be amplified. You want them to be dampened slightly. The flaps will deploy down. And by that, I mean the leading edge flaps will deploy down and the trailing edge flaps will deploy down to give you a little bit more drag, which means you're going to increase your throttle, which will increase your throttle response. And it improves the handling qualities of the aircraft. It makes it, again, relatively seamless. So what's it like to fly overall? It's hard to describe, but I find myself extremely lucky to be somebody that is alive at this time in history to be able to fly the F-22, because they're not making airplanes for maneuverability anymore based on these long-range kill chains that are maybe coming out. And they're not, in some cases, making airplanes with pilots in them anymore. So if any of you guys are working on that, boo. Not really. That's actually a great capability. But flying the F-22 is a real privilege. Captain Don Van Dyke, given the small cockpit real estate required, why not make the throttle quadrant and flight stick left, right, plug and play, depending on pilot preference? Yeah, fair enough. I'm lucky to be right-handed is all I can say on that one, because I don't know how left-handed people end up having to fly this aircraft with their right hand. I mean, the difficulty in that is there is a lot of electronics that goes into those hands-on throttles and sticks. So it's just difficult to move things back and forth is what it comes down to. It could be designed in theory, but that would just increase cost and increase weight potentially. So they decided not to do it. And all my left-handed friends figure it out. So I guess it works okay. So my favorite experience in the Raptor is always doing an afterburner takeoff. An afterburner takeoff, you just hold the brakes, you start bringing the throttles up. You actually can't hold the brakes while at mill power. You'll start skidding along the ground. So you have to let off the brakes while you're pushing into AB. Your afterburner's light in just a couple seconds. And then you have to rotate at like 100 knots and you're off the air at about 140. And all that takes maybe about 4 or 5 seconds. You have to get your gear up as quickly as possible because you're accelerating maybe 40 or 50 knots a second. I don't actually, that's just a made up number. I don't know what the actual number is. And you have to get that gear up before you overspeed them, which is at about 275 knots. By the end of the runway, if it's 8 or 10,000 feet, you can be 500 knots. You can do a high G pull up to 70 degrees nose high, and you can actually still be accelerating because we have greater than a 1-to-1 thrust to weight ratio, which is amazing. Some of the people that are just learning how to fly this jet will accidentally go supersonic in climbs on rejoins over cities, which is usually frowned upon. So some of the testing we've done, I've done some flight sciences testing. Flight sciences is things that you combine things like flying qualities, things like flutter, things like loads testing. It's where you're trying to get up to the edges of the envelope. You're trying to make sure that the aircraft is safe to operate out there. So I've taken a few of these test missions out to, one of the benefits of being a test pilot is the Raptor is limited to Mach 2. So all my operational compadres don't go to Mach 2 because if you go above Mach 2, you're in trouble. But I was allowed to go Mach 2.02. So I like to tell people I've gone over Mach 2, which was pretty cool. And the acceleration profile for that's pretty amazing. So during these high risk sort of flight tests, you want to have a chase with you. So we usually would have an F-16 chase with us because there's a 2-seater and you can put a person with a camera in the back seat. But the 2-seat F-16 turns out significantly slower than the F-22 at acceleration. So what we'd have to do is we'd have to set up me back really far behind and them out in front. And I would have to do this big acceleration profile and try to hit on conditions right as I'm passing them, as they're maybe going Mach 1.3, 1.4, and I'm blowing past at Mach 2, get the test point while they take the picture, rinse and repeat. Much easier said than done. I wasn't that good at it. And then high alpha testing, that's one of the most fun things that I've done. And that kind of goes back to what I was talking about previously. You take the aircraft out and you just point it straight up. And you just wait till it says 0 knots and it just starts falling. And it will just fall through one time and then it'll just start flying. And you're like, that was anticlimactic. Or sometimes you can get it to kind of roll off a little bit and then it'll just start flying, which is a little more exciting. But you can go in there and you can intentionally move the stick around. You can move the rudder pedals. You can do split throttles even to an extent, although that's not, I think you're not supposed to for operational pilots. And it is very hard to make anything go wrong when it comes to high alpha, which is pretty amazing. So if you guys aren't familiar, I'll just give you a little bit of more insight into how we test handling qualities. There's this thing called the Cooper-Harper scale. So it turns out that a lot of handling qualities testing is qualitative. And it comes down to, you can do a lot of tests for things like dynamic pitch response or dynamic stability or static stability. You can run numbers for it and you can get coefficients. And those will tell you generally, maybe this will work right. And you can run them in simulators even. And we do. Every single test flight we did, because it costs $100,000 an hour to fly a test F-22, we simulated once or twice to make sure we were going to not waste anybody's time or waste taxpayer money, basically. But you can figure out what these numbers are and fly the simulator. But in reality, it comes down to, did the pilot like it? So those are things like flying qualities. Flying qualities tell you, is there just a major problem? Is something actually unstable when it should be stable? Or is there just like some coefficient that is just way off? Handling qualities, which is really the realm of the test pilot when it comes to some of these tests of suitability, get into, is it suitable or is it actually safe to fly? So essentially we start in the bottom left. The pilot will initially just go up, hey, I tried to do this maneuver. During this maneuver, was it controllable? Yes, no. If it's no, that's called a Cooper-Harper 10. It's just like, it means control will be lost during some portion of the required operation. I've only ever seen that in simulations. That is never flown. If you see a simulation with the Cooper Harper rating near there, they're never going to put that on a real airplane, and that person might not come back to talk about it. So first, it's controllable. Next is adequate performance attained with a tolerable pilot workload. What they'll do is they'll give you a task and they'll say, hey, I want you to land on center line within the 500 to 1,000 feet at 150 to 160 knots. Your objective is to do this set of constraints, and your threshold is to do this set of constraints, or desired, whatever terminology you want to use. And really, you come down to adequate performance or desired performance. If you can do adequate performance, and I say it was tolerable pilot workload, then we move up to, is it satisfactory without improvement? If the answer is no, we need to actually improve something, we need to change the flight controls, you go over to that 4, 5, 6 range. The answer is yes, you go to 1, 2, 3. Most airplanes actually have a smattering of between 2 to 6, and you just end up accepting that. For example, like if you find that the handling qualities of a fighter with the air refueling door are unacceptable at a certain airspeed, you might just write in the flight control or the flight manual, hey, don't fly at that airspeed, because the test pilot said it's not there. It's not that it's unsafe, just don't do it. I have never rated a clean Raptor above a 3 ever, which means that the worst thing I've ever said about a task is minimal pilot compensation required for desired performance, which is pretty unheard of. The airplane was just extremely well designed, is all I can say.
I just want to jump in for a second on that slide. Bob Harper in Cooper Harper was the chief test pilot at CalSpan right here in the heart of the Niagara Frontier section. Passed away a number of years ago. Great guy.
Absolutely. We have some real expertise up in that region when it comes to flying qualities. So now we'll get into a real world engineering example, open it up for some more questions. So the YF-22 on the right actually looks pretty similar to the F-22. There's some differences, but they aren't notable enough for me to really talk about it. The big things in the real world, it's not trivial to make an aircraft like this handle the way that the actual F-22 does. And the YF-22 flight test showed that missing the tuning can actually lead to poor handling. So I'm going to show you a video of a mishap that occurred on YF-22s. In the video, I want you to pay attention to the flight control deflections to say, hey, I wonder if that was tuned the way that it was supposed to be tuned, and think about whether they're big or small. But before we do that, Steven said, with the weapons on F-22 internal, have you seen a lot of handling issues with other fighters with external stores? Yeah, absolutely. Actually, one of the nice things about the F-22 is that you don't have to do as much testing without having external stores. External stores, like on the F-16, when you get asymmetric loadings, i.e. maybe you have a fuel tank and a bomb on one side, and on the other side is just a fuel tank. Now you have to think about roll stability, lateral stability, susceptibility to out of control that you don't have to think about in an airplane like this. And the handling qualities on airplanes that have external stores, those almost all require some amount of trim, and it changes with airspeed and with loading. So that's one of the things that probably made the problem easier for the F-22, to be honest. Because you're right. Things like the F-16, you have to program in every combination of different stores, or you have to have a flight computer that's smart enough to be able to account for them appropriately. All right, Jimmy Leahy asked, in an operational environment, how is maneuvering affected? Yep, there it is. By external store loads. I think we actually just talked about the same thing, essentially. So the only external stores you can actually put on the F-22 are, you can put fuel tanks on there. When you put fuel tanks on the F-22, it is no longer a 9G capable unlimited AOA airplane. It is now limited to somewhere around 20 something, just a normal angle of attack, because there is actually a potential to go out of control with external stores. But those are the only external stores we put on the aircraft. For asymmetric loads, if you had a center of gravity that was out of control or out of tolerances, like you had a lateral asymmetry, then yes, at a certain point, I can't remember the foot-pounds of asymmetry, then the jet tells you to limit your flight control movements and your alpha to a specific point until the fuel system fixes it. Same thing for longitudinal stability. If you get extremely aft or forward CGs, it changes your considerations for landing, changes your considerations for how many for load. loads. So these apply for nominal-ish conditions, but the nice thing about the smart systems in the F-22 is that it is almost always at nominal because it's such a smart airplane. All right, so we're going to watch the video on the YF-22 mishap. So in this video, what's happening is they're doing a demonstration flight, and they're trying to show off to a few DVs, the F-22. So there's an F-16 chase there. Initially, he's just doing a low approach to the runway, and you'll see him raise his gear, and you can see that he's not in afterburner. You see the flight controls kind of move in a little bit. You see the leading edge flaps just came up. He's going to come back around, and what is going to happen is he's going to do another low approach, and he's going to raise the gear while simultaneously going to afterburner. And raising the gear, remember, changes the flight control gains and some of the flight control modes. We're coming in for approach, low approach. Gears up, afterburner's on. Pilot was fine. The jet was not so much. So what happened? Essentially what happened there is a mode switch pilot-induced oscillation. On the right side, you'll actually see a AIAA paper that was put out in 1996, I think, on the incident. It shows pitch stick, pitch rate, pitch attitude, your Gs, and then some of the deflections for some of the tails and thrust vectoring. What you'll see on it is that essentially the pitch stick where it says full aft is exactly the opposite of the pitch rate, i.e. you have negative pitch rate where you have full aft pitch stick. And then you'll see that he goes full forward stick when you have positive pitch rate. This is exactly what a pilot-induced oscillation looks like. Characteristics of it are, you see how it's flat on the top and the bottom? That means that he is providing full stick deflections. When you get into this full stick deflection period, you are going to continue this oscillation unless you just let go of the stick. And if you'd let go of the stick, it would have actually been fine. The aircraft was statically stable, turns out, but it's a very unintuitive thing to do. So what happened was that as the gear came up, the pitch forces, or the pitch stick position changed its sensitivity to pitch rate. So commanding what seemed to be a small pitch stick force, then actually commanded a much larger pitch stick force. And then he very quickly got to the full stops, and the PIO occurred that you guys saw. So that was something that wasn't anticipated for, wasn't seen in testing through just basic analysis. And we learned a lot from that, actually. This is something that's taught to all the test pilots on all new developmental first flights, how to get out of PIOs, how to anticipate PIOs. But the point is, it's hard to design these systems perfectly. Okay, Justin Kirk asked a question that I was going to get to now. How would the aircraft get out of longitudinal CG given limited stores and automatic fuel management? So all the way from the full fuel loading of 18,000 pounds, all the way down to what you're supposed to land with, which is greater than 2,500 pounds. Your jet has fuel, fuel bladders spread throughout the jet sufficiently that it can maintain the CG in a good range, no matter what the loading is. So if it did have some sort of fuel trapped sort of thing, because that's really what would cause it, i.e. trapped fuel, or a hung, actually even a hung store would most likely not do it because they would automatically change the fuel. But if you had trapped fuel in one position, then you would basically come back with your CG out of limits, and you would just have to do whatever is appropriate for an aft CG or forward CG. But the fuel pumps are extremely good. They can move it from basically not every single fuel tank, but they can move from quite a few fuel tanks to other fuel tanks. And we suck out all the gas, which is great. It's just a really good system that is really good at maintaining longitudinal stability. Richard McKercher asks, what is the process of tuning the control law gains for the various flight configurations conditions look like from the test pilot's perspective? And maybe from the FTE's perspective. So yeah, that's a good question. So F-22 currently is going through some major flight control or major modifications where we're doing some flight control gains testing. And essentially what that process looks like is it's a build-up approach. You start in the center of the envelope where everything looks nominal for the F-22. That might be 300 knots, somewhere around 10 to 20,000 feet. And you will test your flying qualities in that position. You'll do it in a simulator first, after they've validated, first of all, that just flying qualities from a mathematical perspective look like they're going to meet MIL standards. You'll go into the simulator, and the simulators are actually really good for handling qualities, it turns out. Lockheed Martin did a really good job of making this realistic, but we have to actually have different simulators than they have at operational environments to run the realistic loads software that's needed. And by the way, it's getting to 8. Am I good to keep going, or do I need to wrap it up soon?
No, you're completely fine.
Okay, perfect. So FTEs, the flight test engineers, have traditionally been responsible for basically coordinating with the developmental engineers when it comes to flight controls as to, hey, what is the next step from a risk perspective? We'll start low risk and go up to the high risk points. And they will make flight test cards to do that. Yeah, I don't know if I want to get into too many specifics for it, but essentially what happens is we will do flying qualities first. That might just look like things like doublets, if you're familiar with that, or sometimes intentional PIO tests. There's a few other tests we can do to just check out static stability. Then after that, it's usually some sort of tracking task or handling qualities task, i.e., I want you to track a certain type of alpha. I want you to track a target out in front of you to see if that's reasonable. I want you to follow something on the ground. I want you to snap to a position and let me know how that is. Generally, when I'm talking about handling qualities, it's initial nose movement, whether that's with the exception of roll, initial movement, then sustained movement, and then stopping. So if the initial movement makes sense and isn't like a giant overshoot, that's good. If the sustained movement is smooth and doesn't have a giant change from the initial moment, that's good. And if stopping is smooth as well, that's good as well. Essentially, you don't want to see a lot of oscillations in an underdamped system. You want to see maybe something that isn't perfectly damped, but it's pretty close or is relatively smooth, so that way you're not getting oscillations as you're trying to get to specific points. Sorry, hopefully that answers your questions. All right, the Raptor demo. So you've already seen a couple of the slides on this one. I won't go into all of them. When the flight controls work, it's great. When the YF-22 experience doesn't happen, which that has not happened. We haven't had any PIOs or any crashes like that. We have had a few nose or landing gear collapses, which you might have seen in the news, but that is not related to the flight control system. Landing gear system, maybe not so good. So for the Raptor demo, and to be clear, the landing gear system is actually fine. It's just that's the thing that has had issues on landing. When everything goes right, it is amazing. So a few maneuvers that are cool. The pedal turn we've already talked to. The tail slide is actually a maneuver that essentially only test pilots and the demo folks can do, but that's essentially high angle testing. You just point up, go back to mill power instead of afterburner, so your thrust to weight is reduced a little bit. You let your airspeed slow down to 0, and then you just kind of start flying backwards. And due to the thrust vectoring, most airplanes, what would happen is you start falling off. But due to the thrust vectoring, you kind of hold on to this attitude a little bit longer than they can before you fall off, which is pretty cool. The Cobra turn, you might have seen this with some fighters like the Su-27, Su-35, but you can be going really fast. Pull full aft on the stick, it'll limit you to 9 Gs. You'll get a bunch of vapor potentially on the back as the airflow separates. And then you can push the stick straight back and then push it straight back forward, slow down really quickly. J-turn is something that we use quite a bit actually in fake dogfighting. So if somebody's behind you and they don't have the ability to go to maneuver in high angle of attack ways that the F-22 can, and things like the Su-27, Su-35, F-35, you could pull up really high, get to a point where you're high angle of attack, and then put in pedal like this, and basically just turn right back around at them. Actually, don't know why they call it the J-turn, to be fair. It's more just like a turn up like that. You need to think about it. Slow speed passes, you can get your nose up really high. You can hold it high. When you think of things like slow flight for a Cessna, maybe you're getting down to like 50. I haven't flown a Cessna in a while, but you're getting down to like 50, 60 knots. In the F-22, maybe slower. In the F-22, you can fly this airplane, which is, 70,000 pounds, also at about 70 or 80 knots, which is pretty cool. So really, it's just the really smart engineering plus a little bit of black magic equals a really awesome military capability that enables the pilots to succeed is what it comes down to. And that was really captured in my first time fighting F-16s. I was a brand new B courser going out to fight some experienced F-16 guys who were Red Air for us. We're going to do air combat maneuvering, which means we started 20, 30 miles away. And we just turned in fights on, me and my flight lead against 4 of them. We turned around and we flew this 5 times. Every single time I killed them beyond visual range without them ever finding me. So that just speaks to the mission systems in it. But then we would continue for training and do some fighting with one of them. And me, a guy who's never flown before, was still able to get to an offensive position on some of these guys, and still very capable airplane, the F-16, because of the really amazing really flight control programming and work that folks have done to make this airplane so good. Stephen Tower, have you engaged F-35s also now for training? Yep, F-35s are a better capability than they're often portrayed to be, is what it comes down to. The F-35 is capable, because of its flight controls, of doing a lot of things the F-22 can do. Sure, it doesn't have vectored thrust, but it can do things like pedal turns, which you'll see in demos. It can do things like pretty tight loops, and it can pull 9Gs. Now, is it as good as the F-22? Not a chance, but it's still a capable airplane. I'd say that it has its benefits, especially in high alpha fighting, but it's just a little bit heavier and a little bit less capable. Santiago Perez, have you had a chance to experience the F-35 helmet mounted display system? Only in the simulator. I haven't flown the F-35. So yeah, one of the things about the F-22 is it doesn't have a helmet, which is we're trying to fix right now, because we're the last fighter that doesn't have a helmet. But that's because it's been so successful at killing things beyond visual range or defeating enemy aircraft that people said, hey, that's not that important. We've got stealth. We've got a really good radar. We've got really good systems on the airplane. So why do you need a helmet to see folks around you? It turns out it's helpful for other things like formation keeping. It's helpful for some of these close-in fighting sort of things. So we might get one in the future. But I would love to have something like the F-35 helmet mounted display, to be clear. Henry Spencer, flying unstable aircraft in World War II, some of the photo recon versions of Spitfire had a tail tank to increase range were unstable until that tank was empty. Needed concentrated pilot attention. Yeah, exactly. So I didn't know that. I didn't know that actually they had unstable aircraft that were designed to be unstable. It just requires you to consistently, or even just like neutrally stable airplanes that would just continue to move up at the same rate. It just requires you as a pilot to be in the loop the entire time. Whereas in the F-22, you can take your hands off the control, look down at your displays, shoot some people, play your video game of beyond visual range combat, look up and the airplane is still going to be flying perfectly fine. But that's a really cool story about the Spitfire. I didn't know that. All right, biggest takeaways. We're getting towards the end. Reckless abandon is actually nearly possible, even in a high alpha 9G fighter, which is pretty cool because this thing has a giant, basically envelope in place that can be employed in. And I, as a pilot, barely have to worry about it, which is really amazing. Advanced fly-by-wire generates unheard of maneuverability and the capability to do things like the F-22 demo shows you, which other airplanes
just straight up could not do. Now as other airplanes are getting advanced fly-by-wire, you're going to see it, but the F-22 will still have some advantages in that it's got just a really great thrust to weight ratio, and it was designed for dogfighting. Carefully tuning the cockpit stick and flight controls improves handling qualities, and the handling quality is what it actually really comes down to. Is, hey, does the pilot find this acceptable without improvement? And if that's the case, then we're good to go. Or if it's not the case, maybe we need to think about changing something. And then a wide envelope with a lot of different modes, such as landing, takeoff, air refueling, cruise. It requires, and high alpha flight, high G flight, supersonic flight. It requires wide consideration of variables. And you have to have some really smart engineers to make an airplane fly the way the F-22 flies. What it really comes down to is reducing pilot workload, helps pilots complete other tasks, which makes the F-22 the most effective air dominance platform. All right, guys, that's what I got for F-22 flight controls. Open it up for any other questions. Being from Canada, I have to ask, where did you get the handle bobsled? Good question. You know, you don't get to choose your call sign, is what it comes down to. The short story, and there's always a longer story, is in a fighter, if somebody shoots you with a missile and you just fly straight into it, it's called sledding. You just sledded today. You just weren't looking out. You weren't like figuring out what's going on. If you're pointed at the threat, you're hot to the threat. If you're pointed away from the threat, you're cold to the threat. So I was at a simulator as a young wingman, and I was fighting my instructors, and somebody messed with my systems, and I thought I was targeted. I wasn't targeted. It's a stealth airplane, it turns out. They had shot some missiles. I turned around. Missile wasn't even tracking me. And somehow, very luckily, I hit it going cold. So I sledded cold. So that's why it's bobsled, is the story that I'm clear to tell you. What else? All right, Allison Mangano. As an Air Force test pilot, are you a civilian or do you have to enlist to attend the school? So I've been an officer in the Air Force since 2011. I did ROTC in college. So most of the people that go through test pilot school are officers in the Air Force. About half are pilots and about half are flight test or pilots or navigators or WISOs or other rated officers. And about half are flight test engineers, maybe a few less. But almost everybody is a rated officer, with the exception of we have 1 to 2 civilians go through as flight test engineers every year. So if anybody's looking for a cool job, get out to Edwards, become a flight test engineer, do a great job, and you can apply to test pilot school and get to fly in a lot of cool airplanes, work on some cool stuff.
Okay, I actually have a question, just save until the end. The second program I ever worked on as an engineer, longer ago than I care to admit, was a study to recommend the type of gun that should be put on what was then called the Advanced Tactical Fighter. Because the F-15 wasn't even supposed to have the M61, so they were damned if the ATF was going to have the M61, which, for those who aren't familiar with the guns, it's a 6-barrel, 20-millimeter Gatling gun with about a 6,000 round per minute rate of fire. We ended up recommending something more that's like in the F-35, which is a slower rate of fire, but it's 25 millimeter. So are you happy with the M61, or do you wish it was a different kind of gun?
You know, there's pros and cons to both. For air-to-air fighting, I think the M61 is great. It's as good as it can be. Tell you, 6,000 rounds per minute or whatever it is, goes by really fast when you only got 500 rounds in the airplane. You only have a few seconds essentially to shoot. So usually it's like 3 trigger pulls is what you got. The F-35 one, they have fewer rounds, and I don't know actually if they have more or less time, but I think it's about the same. And I think when it comes down to it, there's not a big difference. Now for air-to-ground stuff, I think I'd probably want the F-35 gun, but I'm not doing that in the F-22.
Okay. And just a quick follow-up question. Are you glad it has a gun? I mean, if you get in a knife fight, you've kind of screwed up.
Yeah.
In the grand scheme of employment, in retrospect, now that the plane is fielded, would it be better off if the weight was used for something else?
You know, there's often this debate that we're moving towards this intelligentized version of warfare where everything is going to be solved. You're going to have sensors that work. You're going to have weapons that work really far away. You're going to be able to figure things out very easily, and like the need for uncertainty in warfare is going to go down. I'd say that's the opposite. The truth is, everything that you do to improve your sensors or improve your weapons, the adversary is doing something to try to stop you from getting that sensing or stop your weapons from having effectiveness. They don't call them hittles. They call them missiles. Sorry. But I think that there's still a need to have a close-in fight capability. The gun, I mean, I could be convinced that the AIM-9X is good enough, but you need something to fight close enough. And the gun has been very helpful for the last few years. So I would say I'm neutral on the topic.
Okay.
Who else asked here? Let's see.
You have two, I think.
Okay. Allison, actually, I think all the way up here. Allison Mangano as an Air Force. Nope, you already talked to that one. Justin, were you able to recover the engine you had to pull to idle? Yeah, I just had a high oil pressure on one engine, so I just had to keep it in idle, and I just flew all the way home. One engine, and the handling qualities were exactly the same, essentially. Just had to keep it up a little bit higher. You can actually air refuel and mill power on one engine. You don't have to have two engines to accelerate, which is pretty cool. So yeah, we made it home, good to go. And the engine stayed on. Allison, how do you apply to the program as a civilian? Yeah, so you have to be an Air Force civilian. And actually, I noticed that I think someone in here said they were Canadian. I can't remember who. But we actually accept flight test engineers from other nations too. In my class, there was a French guy, there's Singaporean, there was supposed to be a Singaporean guy. I think he ended up not getting there. There's a Canadian that was in my class. And every class changes, but we have a wide range of folks that come to test pilot school. And when you look at folks outside of the US military and government, so big picture, it's a combination of military and government folks. For pilots and flyers, it's all military for the US Air Force Test Pilot School. But for FTEs, they have some civilians there. Let's see. Richard, you mentioned the control mode switching, such as the pedals commanding side slip angle at high speed and yaw rate at low speed. Take any time to get familiar with the feel of the control mode switching. Yeah, absolutely. For example, there's even more rules to it than that, and I can't get into all of them. Specific angles of attack, even change which mode happens. That's one of the first things that you're taught about whenever you start flying this airplane, because there's some very good heads-up display cues as to when you're max performing the aircraft, i.e. hitting the CL max angle of attack. You want to hit that most of the time, except when you want to go above it to execute some specific maneuvers. And there's a specific range that gives you the best sort of flying qualities in there. So it absolutely takes time to get familiar with the control mode switching. But to your question, does it take time to get familiar with the feel of it? I'd say that there is actually very little noticeable change in the feel of the control mode switching. It is very seamless. Pitching is seamless when it changes from pitch rate to G rate or to G command. The yaw stuff is requires a little bit more training and kind of practice, but it's still relatively easy to figure out. Justin asked, how'd you get to fly the P-51 and B-17? Went to test pilot school, and they let you fly a bunch of cool airplanes at test pilot school is basically what it comes down to. So we went and flew the B-17 to see what it's like to fly an old airplane that has old engines, that has some interesting handling qualities, which was pretty cool. And the P-51, we got to go out and pretend we were World War II fighter pilots and get to do some cool fighter pilot tasks representative of what they were doing whenever they were testing it back in the 40s. Joe said, can you talk about the important factors in tuning how the control system switches between pitch control and G control? Sure. So every aircraft has a structural limit to it, i.e. a limit that you don't want to exceed to have structural damage. In the F-22, that limit's 9 Gs. Below a certain airspeed, you actually can't hit 9 Gs. You would hit the stall or CL max before you actually got to 9 Gs. So below that limit, you can pull the stick all the way back. And even if I didn't have a flight control limiter on it, I wouldn't over G the airplane. But above whatever airspeed actually allows me to hit CL max, or whatever airspeed enables me to actually hit 9 Gs, it's going to have to limit me to 9 Gs. So essentially, they just choose an airspeed that is below below where G control, where pulling the stick all the way back causes an over G. And it turns out that pitch control is a better, it resulted in better handling qualities for low speed fighting. You don't actually have to choose a pitch control centric system ever. You couldn't actually keep it G control the entire time. It just turned out they found out that, hey, if you change it at this airspeed that's, below the point where you hit 9 Gs to pitch control, then the pilots find that they do better on these tracking tasks that they would need to do in basic fighter maneuvers. So now we need to blend that in to where it's seamless, i.e., hey, 10 knots above this, it's G control. And then as I decelerate through this speed, it seamlessly switches to the exact same pitch. And when I say pitch control, it's actually pitch rate control. Sorry, pitch rate that it had right then. So that way it doesn't do something crazy or it doesn't have like a giant step function where it changes significantly. It's basically just coming out of handling qualities and flying it in the sim and seeing what works right. Allison Mangano, flying at these speeds, doing flight test movements seems like it would be very intimidating. Are you ever scared? If so, how do you handle that fear? I would like to say no, but honestly, yeah, going Mach 2 doesn't really feel comfortable in flight test. Because if something goes wrong, you can't eject, because you can't eject above maybe 400 or 500 knots without high potential for injury. And we're often doing this testing well over the water to stay away from folks. You can't go supersonic over land except in some specific places like Edwards Air Force Base and a few other test locations. So especially in those times where you're doing high speed, really remote, edge of the envelope loads testing, yeah, I think I've been concerned. And the way that I mitigate that concern is by talking to my flight test engineers, getting the predictions for what's going to go, and then flying in the sim multiple times to make sure that I'm ready to do it. And then we also spend a lot of time briefing contingencies, and briefing through those contingencies turns it more into, hey, this is our decisions of what's going to happen if something does go wrong, and this is how we're going to mitigate it. We also regularly do emergency procedure sims. So handle the fear through basically intense training and preparation. Justin Kirik asks, have hypoxia problems been resolved? Yep. Yeah, we haven't had hypoxia problems in a while, which has been great, because I know that was a huge deal, especially when we got on, I think, Good Morning, 60 Minutes or whatever it was at the time. We have largely resolved them. When I say largely, sorry, we have resolved them. Yep. What else?
Oop. Okay, I'm going to let this be the last question, because Tucker has a family and little kids, and unless you want to keep going, we'll make this the last questions that are up now.
Yeah, sure. No, I'm okay. My 3-year-old goes to bed at 6 o'clock, which is nice.
Okay.
So
This is
12
great.
hours. Yeah.
People can leave when they want. We'll press. Great.
With the implementation of AI with the Vista, where do you see the future of fighter jets, including the NGAD? We'll see, is what it comes down to. We need to see how AI actually works. I don't know how many of you guys have computer science backgrounds, but I think that there's some things that we just haven't seen demonstrated that you're going to need in combat. And the uncertainty of combat is a much more difficult environment than some of the test environments where we've looked at some of these capabilities. I think we're absolutely looking at things like collaborative drone aircraft augmenting us, and that's going to be cool. But we'll just have to see how these other things do in tests. And NGAD will be cool too, hopefully. Glitvic Memoria, what are some unique challenges faced by test pilots testing digital aircraft today compared to pilots during the mid-1900s? There's a lot more technical rigor to what we're doing. So if you look at, and not just technical rigor, I'm very lucky to actually be a test pilot when I am right now. The mortality rate for test pilots during the mid-1900s was probably 20 to 50 times higher than it is nowadays. I just made that number up. Don't quote me on it, but it is significantly higher back when they were doing early testing of jet aircraft, for example. Nowadays, we do so much risk mitigation and so much simulation that's relatively high fidelity that we don't have to really be as concerned. Whereas back in the past, we think of tests sometimes in these little buckets of fidelity. Maybe at the bottom is things just like software simulations, maybe hardware in the loop, some other type of simulation, all the way up to real world employment or real world flight test, where real world flight test is the best fidelity. And back in the day, they didn't have all these intermediate steps that allowed you to get fidelity before. So if you wanted to go see if your airplane handled at Mach 2.5, you just had to get up to Mach 2.4 first and see if it works, and maybe go to 2.5 next. We can model that really well, which is great. So things that I have to face nowadays, that's different. Test pilots nowadays are focused actually a lot on mission systems. So this is the cool stuff. This is flight controls. This is flying qualities. I love this stuff, but I'll tell you the vast majority of things that I'm testing are upgrades to the radar, upgrades to everything else. Hey, yeah, thanks. If anybody's dropping off, I really appreciate you guys taking the time. Upgrades to the radar, upgrades to the sensors. I have to be really smart when it comes to a variety of engineering disciplines, electrical engineering, mechanical engineering, aero engineering. You have to have a little bit of knowledge of each to be able to talk effectively to all of the engineers. So I think that's a challenge that we're facing. Does the F-22 have GCAS yet? Yes, it does. And it is working good, which is nice. That's been a win for the last few years. Does the risk mitigation you talk about ever get in the way of actually testing the aircraft to the maximum extent? I don't think so. Sometimes I would argue that sometimes I can feel like we're being a little risk averse. We could test things quicker in certain instances. There's still, you're not in combat. There's no pressing need to go test things. Let's just test, a little bit away from the happy zone in the middle of the flight envelope at a time. I think we could sometimes take bigger steps and that would be fine. But in general, no, we get to the maximum limits because we have to give the warfighter the full envelope of the airplane. We just might do it a little slower than we would if we accepted more risk. Yep. I also am looking forward to technology NGAD's going to bring. Richard, from your perspective, what qualities make a flight test engineer effective at their job? Yeah, so if any of you guys are thinking about being a flight test engineer or working in the aviation or fighter, well, it doesn't have to be just fighters, actually. Flight test engineers work on a variety of things, and I work on a variety of platforms as well. I think that there's some Air Force qualities that we throw around, like humble, credible, approachable. I think those are really good. Be humble. That's number one thing. I don't like to go around and tell people I'm a F-22 fighter pilot because in reality, a lot of other people could have done this job. I just got lucky. Be credible, be good at your job, and be approachable and be easy to work with. Like, we're all on the same team and we're working on an important mission. Those are the three qualities that I look for in folks that I work with. And what's your favorite civilian aircraft you've flown? I actually haven't flown that many civilian aircraft. It's been mostly military now that I think about it. I've done the sims for the A320. It's almost like flying, like the full motion sims. You get to log it in your flight book. I'll say that's my favorite civilian aircraft. I think that thing is really cool, and the digital flight controls they have in that stop people from doing dumb stuff is awesome. So I'll say that.
Okay. Okay, I think you exhausted all the questions. No, last P-51 question.
Yeah, absolutely. P-51, outstanding. I was very lucky to fly that airplane. It was ahead of its time. Very fast, very maneuverable, very fun.
Yep.
Hey,
Well,
thanks so much for having me.
This was terrific. This is a terrific presentation. You made my job a lot easier because you fielded all the questions yourself in real time. And for the people who are still hanging in there, we have never had so many good questions. So, I mean, you guys were great. This was just terrific. And the talk was recorded. If, yep, someone just asked, was it recorded? So send an email to that email I showed up before, nf.aiaa@gmail.com. And a couple of hours, it takes Zoom a while to process the recording, but certainly by tomorrow morning, we will be able to send out a link to the recording. So novemberfox.alpha@gmail.com. And I will send you a link to the recording. Tucker, again, thank you so much. Terrific talk, terrific audience. And everybody have a great evening.
You too. Hey, thanks again.
Bye, everybody.